Okay, so I'm going to go through the notes, the rest of these notes with you guys, and as requested by Billy Beesman, I will prove the derivative of e to the x. So I'm going to use the squeeze theorem to do that. And if you use your calculator, you'll show that this right here by the squeeze theorem, um, this right here is equal to 1. So if you want to check it with your calculator, just take your calculator out, type into y1, type in e to the x minus 1 over x, and then go to your table set and let delta table be 0.001, and let your table start be 0. And if you do that, you'll get 1 for this right here. So now let me prove this. We're going to go the limit as h approaches 0 of f of x plus h, which would be e to the x plus h, minus f of x, which is e to the x, all over h. And then what I'm going to do here might seem a little weird, but I'm going to take this problem and I'm going to try and produce this over here using the squeeze theorem, that equals 1. I'm going to do something pretty awkward here. I'm going to divide everything in the top part of this problem by e to the x. Okay? So I'm going to take and multiply top and bottom by 1 divided by e to the x. And I'll do the same thing on bottom. It'll be 1 divided by e to the x. So we'll have the limit as h approaches 0. If I distribute this, we're going to have e to the x plus h divided by e to the x minus e to the x divided by e to the x all over h times 1 over e to the x. And you probably see where I'm going with this. I'm trying to produce this, and the way that I thought about this is I need to get 1 here. So if I divide e to the x by e to the x, I'm going to get 1. I need to get e to the h. If I divide these two right here, I'm going to subtract the exponents. And what I'll end up with is the limit as h approaches 0 of e to the x minus 1 over, sorry, be e to the h. It'd be e to the h, my fault. Erase that. Because I'm going to subtract. When I subtract these exponents, I'll subtract the x's. So it'll be the limit as h approaches 0 of e to the h minus 1 all over h. And then I can have this part right here, this 1 over e to the x, I can just multiply by the reciprocal of that, just have e to the x. This right here, the limit of this right here will approach 1 by the squeeze theorem, and then you end up with 1 times e to the x. So you end up with this as 1 times e to the x, because the limit as h approaches 0, there's no h to plug into here, so we'll treat e and x. E is a constant, but we'll treat x like a constant, so we get 1 times e to the x. So there we get e to the x, there's the derivative. So that is the proof for e to the x. The derivative of e to the x is e to the x, so there you go. So now let's look at these examples. We went through the derivative rule in class, so let me go through them now with you, and I'll go through them again. The derivative rule for e to the x, derivative of e to the x, e to the x. With the chain rule, it's derivative of e to the u will be itself times the derivative of the exponent. So if I'm looking at this first one, it's going to be y prime. So it'll be itself, so just copy it down. Times the derivative of the exponent, which would just be 1 plus 2x. And if you want, you can throw the 1 plus 2x out front. And we'll have times e to the x plus x squared. And that would be the same, just to do one, so there's that answer. That would be the same. It wouldn't matter what this exponent is, because some people are asking, what about if it's e to the 3x or e to the negative 3x? Well, it's the same rule. It's y prime is going to be equal itself, so just copy it down, times the derivative of the exponent, which is negative 3. So then the answer would just be negative 3 e to the negative 3x. So that's how you would do the derivative of e to the negative 3x. Going on to example 2, find the derivative of dy dx, be y prime is going to be equal to derivative of e to the negative x squared would be itself, e to the negative x squared times the derivative of the exponent, which is negative 2x, plus this next part, constant multiple rule, will just go 2 times the derivative of e to the negative x, which will be itself, times the derivative of the exponent, which is -1, and then the derivative of a constant is just 0. So final answer will just be -2x e to the -x squared. This negative can go out with the positive 2, make it -2 e to the -x. And one of the things that we'll do down the road is we'll start factoring out powers of e. But for right now, we're going to leave that alone. But later on, we'll start factoring out powers of e, and I'll show you how to do that as we get closer to that. The next rule is for your a to the u power. So derivative of a to the x, we'll just skip right to a to the u. It'd be a to the u, derivative of a to the u is a to the u times du dx, and you've got to remember to multiply by the natural log of the base. So example 3 would be y prime is going to be equal to itself times the natural log of 2, don't forget that, times the derivative of the exponent, which is 3. And then we can rewrite this and bring this out front. Now, do not make the mistake of saying natural log of 2 times 3 is natural log of 6. That's not correct. You can bring that 3 to the front of it and have 3 natural log 2 times 2 to the 3t. And then what we can do here is this is to the first power. We put the monkey back in the tree, so that'd be natural log of 2 to the third power times 2 to the 3t, which is equal to natural log of 8 times 2 to the 3t. And there's your derivative. The next problem, example 4. At what point on the graph of the function does y equals 2 to the t minus 3? At what point on the graph does the graph of the function, does the tangent line have a slope of 21? So in other words, I want to figure out when the slope of the tangent is equal to 21, or when the derivative is equal to 21. So what I'm going to do is I'm going to take the derivative and then set it equal to 21. So I'll take this right here, y prime would then be the derivative of 2 to the t is just 2 to the t times natural log of 2 times 1. And then derivative of constant is just 0. So my derivative cleans up a little bit. It'd just be natural log of 2 times 2 to the t. Times 2 to the t power, not 2t. 2 to the t power. That's a dx over here. Now I want to figure out when this equals 21, so I just set the derivative equal to 21. So 21 equals natural log of 2 times 2 to the t power. And this is a good review of how you solve an exponential equation. So I divide both sides by natural log of 2, so I'm going to have 21 divided by natural log of 2 is equal to 2 to the t power. And if you remember, you have to take the ln of both sides. So I'm going to have ln of 21 divided by natural log of 2 is equal to ln of 2 to the t power. Then I can pull the monkey out of the tree. And we go here. So I'm going to have natural log of 21 over natural log of 2 is equal to t, pull the monkey out of the tree, times natural log of 2. And then I divide by natural log of 2. And by the way, you can separate this property. If you want to separate this with subtraction, you can go natural log of 21 minus natural log of the natural log of 2. And then I divided by this natural log of 2 for my final answer, and that equals t. So that would be where the slope of the tangent line is equal to 21. Whatever that value is, you'd have to plug it in your calculator, which certainly is going to be a decimal. All right. So then we move on. I'm not going to prove the derivative for natural log x, but you certainly can run it through the alternate form of a derivative and prove it as well. And you're going to end up using some properties there of logs probably. The derivative for natural log x is 1 over x, but for chain rule it's 1 over u times du dx. So we're going to have dy dx. Here it's going to be 1 over x squared plus 2x minus 1. That'd be your 1 over u part times the derivative of u, which is whatever is on the inside there. So that'd be just 2x plus 2. And so your derivative, you can factor a 2 out on top if you want. Make that 2 times the quantity x plus 1 over x squared plus 2x minus 1. And you don't have to factor out that 2. That's entirely up to you. There's your derivative. Nothing to it. Next one, this is a derivative of natural log with a chain rule. And what happens here is you got really 3 functions. You've got a function on the inside, f of x, which is x squared. Next function is your sine x. And then your third function is your natural log x. So this is really h of g of f of x. If you find its derivative would be h prime of g of f of x times g prime of f of x times f prime of x. That would be how you do the chain rule in this. So the outside part is the natural log. And this is not a product because you don't see two variables here. You've only got one variable in the equation, so there's no way it can be a product. So you can see it's a composite. So it's y prime. It's going to be natural log. To take the derivative of natural log, we're going to go to my natural log rule. It's 1 over, okay, it's 1 over sine of x squared. And then times the derivative of the inside, which you also have to use chain rule for. So it'd be times cosine of x squared times 2x. So final answer is going to be 2x cosine of x squared over sine of x squared, which you can, this right here, oh sorry, of x squared, sine of x squared. You can right here make that cotangent. And I'm sure they might do that. So it'd be 2x cotangent of x squared would be another possible answer for that problem. So there's that problem, example 6. So moving to the last derivative rule. Example 7, I think I'm just going to skip because I think if I remember this, I don't have all of the information there. So go down to the last two examples here, derivative of log base b of x. Now I had a mistake here in the notes, so I fixed it. In your notes it says natural log of u, but it's supposed to be natural log of a. So find example 8 and 9 here. So when I find the derivative of this, this is a problem where before I even take the derivative, it looks kind of complicated. There is a, remember, rewrite, differentiate, simplify, prep the pizza, make the pizza, clean up the pizza. You can actually simplify this problem first, and it actually is not even a log, because log base a of a just cancels. So you're just left with sine x. So this problem is not even a log problem. It's just a problem disguised as a log. So that problem doesn't require your log rule. This one over here will. Dy dx is going to be log rule, okay, log base 2. It's not natural log anymore. So log base a, it's going to be 1 over u, just like the log rule. Natural log rule was, so 1 over x squared plus 1 times the natural log of your base, so natural log of 2, times du dx, which would just be 2x. So we'll end up with 2x. A lot of times they'll throw the natural log out front, x squared plus 1. And there's your derivative. And hopefully that helps with the homework that you're going to take a look at. Now, I don't know about that example 7. I'll have to take a look at it tomorrow.